Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In this episode, we'll discuss some techniques for numerical integration. Many integrals cannot be computed analytically. As a matter of fact, one could say that the vast majority of integrals cannot be computed analytically, that if you just randomly throw some functions into an integral, for example here on the right, and there's no reason to believe that we can solve that integral, solve the area of the curve analytically. We might be able to use Taylor series in some cases to get approximations, but in general we're not going to be able to evaluate definite integrals analytically for the vast majority of functions that would be randomly thrown together. However, we can approximate the area under the curve. We recall the idea of Riemann sums, where we drew rectangles that were based on the function values of a curve. In this case, we've drawn rectangles at the left end of each interval. We take the y value at the left end of the interval. We make a rectangle, in this case of width 1 in each case, and then we do so at each integer value of the function here, and we see that our rectangles lie below the curve on the left side, and then our rectangles lie above the curve on the right side of this for this particular function. So we have errors. That's the area between the rectangles and the curve. In this case, there'll be some cancellation because some of our rectangles lie below the curve, some lie above the curve. And we note that as the width of our intervals gets smaller and smaller, the approximation to the area under the curve gets better and better. We're dealing with functions that are continuous. We consider that the intervals, the width of each rectangle is going to 0. We could use the y value at the left end of any interval. We could use the y value at the right end. We could use midpoint values. We could use a random value on each interval, a random y value, and different y values for each interval. That we could do it in the midpoint on this interval, the right end on this interval, the left on this interval, etc. And as long as the width of the intervals are going to 0 and the function is continuous, we will eventually get closer and closer to the true area under the curve. Well, we can improve on using rectangles by using what we have learned in polynomial approximation, and we can take piecewise linear segments. And when we take piecewise linear segments, the red line segments, we note that we find trapezoids. We can write the function on the line segment, linear approximation to the curve on any interval, on an interval from A to B. We just use the Lagrange polynomial, and we can integrate that function on the interval, and we will end up, well, it's a trapezoid, so we're going to end up with the trapezoidal rule, which is 1/2 the height. In this case, we turn it sideways, and we get the height is the right end of the interval x value minus the left end of the interval x value. So you have 1/2 height times f of b plus f of a. That's the height of the curve at the two ends of an interval. So that's the area of a trapezoid. You could do it analytically just by taking the integral of our line segments. Let's consider an example. We'll take the same curve as we had before, but now on a smaller interval. We take y equals 1 over 1 plus x squared from -1 to 1, and we'll just draw two line segments. We know that the y value of the curve at x equal 1 and x equal -1 is just 1 over 1 plus 1, or 1/2. And when x equals 0, the y value is 1. And we're going to use the trapezoidal rule. What do? We take 1/2 the width of each line segment zone is 1 in this case. So we have 1/2 times 1, and we add f of a plus f of b. So we add 1/2 plus 1/2 in this 1/2 plus 1 for the left trapezoid, and then we add 1 plus 1/2 for the right trapezoid. So right, we have 1 half times the width of each interval, and in this case our intervals have the same width, so we could pull out the 1 half b minus a, and then we have the function at the left plus the function at the right, plus again the function at the left minus plus the function at the right. And so we note that we're going to get twice the middle value because each trapezoid or each interior part of a trapezoid is going to be used twice in this method. So we have 1 half times 1 times a half plus 1 plus 1 plus a half. We put that together, we get 3 halves, and the true value is arctan of 1 minus negative arctan, or minus arctan of negative 1. So we end up with 1.57 pi over 2. And again, we stress that the interior points are used twice. So in general, if we have a situation where we're using a lot of trapezoids, we break the interval where we want the area of the function into lots of subintervals. So we're going to take each trapezoid f of x0 plus f of x1, f of x1 plus f of x2, etc. Well, the interior points are used twice, and so we have the width of the interval times a half times f of x0 plus twice each y value at the interior plus once times the function at the very end. And we note that this method better be exact for lines because we're using trapezoids, which are lines. It turns out the error is going to be like h squared, where h is this interval width. And we can consider, for the same function as we just noted, the integral of 1 over 1 plus x squared, in this case from minus 5 to 5. With h equal 1, we get the following approximations as we take h smaller and smaller. And we note that as we take more and more approximations, that as we have the interval size, that the ratio of the error goes down by a factor of 4. This is the old error divided by the new error. And after we have the interval size several times, we note that we're getting 4 times as good or of an estimate for the area under the curve. Well, rather than using piecewise linear segments or rectangles, we can use piecewise quadratics through 3 points. And we can write out our Lagrange polynomials, and we can integrate from a to b, and if we have points a less than c less than b, so we have 3 points on the interval, and if the points are equispaced, we'll say that the x value at the right end minus the x value at the left end is 2h, so the distance between b and c is h, the distance between c and a is h, and so the whole width of the zone that we're dealing with will be with 2h, and we can work it through and we'll get that the area is approximately h over 3 times the function value at the left plus 4 times the function value in the middle plus the function value on the right, and that's called Simpson's rule. We'll perform the same example as we did before. We're really approximating the curve 1 over 1 plus x squared by a parabola, by a quadratic. And what happens when we do that? Well, we have h over 3. H is 1. That's half the width of the whole zone. H is 1, so we have 1/3 the function value at the left, which was a half, plus 4 times the function value in the middle, plus the function value on the right. And so we have, inside the brackets, we have 5, so 5 over 3. And the true value again was 1.571. Turns out that Simpson's rule was worse for such a wide interval, but in general, Simpson's rule will be better, and as we'll see in a moment. And for multiple subintervals, we would do the same thing. We'd have f at the left end plus 4 times f at the middle plus f at the right. And then the next interval would have the points x2, x3, and x4. Note that f of x2 is going to be used twice. So we're going to get 2 times the function value at x2. Similarly at x4, x6, and x8. And we'll get the formula that the area is approximately h over 3, f of x0 plus 4f of x1 plus 2f of f of x2 plus 4f of x3, and so forth. We go 1, 4, 2, 4, 2, 4, 2, 4 till the end, we get 4 again, and then 1 of the last point. We note that n better be a multiple of 2 for this to work out, because we're using the points from 0 to 2, 2 to 4, 4 to 6, etc. Let's go back to our previous example, the integral of 1 over 1 plus x squared from minus 5 to 5. And we're going to use Simpson's rule in this case. So in the case where h equal 1, we would have 11 points. X is x0 at the left and x is x10 at the right. And we use Simpson's rule, and we plug it in, and we have the intervals as we did before, and the errors go down very quickly, and as we get closer and closer to the true value of the integral, the errors go down by a factor of 16, rather than for the trapezoidal rule where the errors went down by a factor of 4. So in that case, they went down by like h squared. We have the interval size, we got a factor of 4 improvement. Here, if we have the interval size, we get a factor of 2 to the 4th, or 16, a factor of 16 in reduction of the error. You can take a moment for some math culture. And there was a chemist, a physicist, and a mathematician who ended up being stranded on a deserted island. They had plenty of water from a freshwater spring, and there were some trees around, but the only food source they found was several cases of beef stew. And it was canned beef stew. So the three men were trying to come up with a way to get the cans open. The chemist said, well, we know that most material expands when heated. Let's build a fire. We can place the cans in the fire, and the increase in pressure caused by the expanding food will rupture the can, and we'll all be set. No, said the physicist, it would take too much work to get a fire going, and even if your idea worked, we would have beef stew spread all over the campsite. What we should do is place the cans on a large flat rock, then drop a second heavy rock from a tree on top of them. The kinetic energy of the falling rock would be transferred in a non-elastic collision to the cans, which would crumple and split open. But, the mathematician objected, that's no good. Even if it worked, we would have dirty beef stew smeared all over a rock. No, the solution to the problem is quite simple. First, let's assume that we have a can opener. I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.